Hi, for our project, we chose our architecture to be inspired by the GPU. Our presentation is split into 3 parts. First, we're going to walk through where we're starting from. Then we're going to go through our design decisions. And then finally, we're going to go through our implementation. Let's start with quickly reviewing how matrix multiplication works. First, we need to take the elements from the first row of the left matrix A, and then we need to multiply them with the elements in the column of the right matrix B. We will then store their sum in a corresponding row and column in matrix C. This is done for every element in matrix C. Next, we would like to note some observations we made on the n by n matrices. At n equals 2, n equals 3, and n equals 4, we noted these counts and extrapolated to n. We'll need some of these values for later. Next, let's take a look at some limits. Assuming we want to use 8 bits for all of our matrix of values, that would mean at most we will have 256 values. The largest 8-bit value we can then multiply without overflowing is 16 minus 1. The largest 8-bit value we can then add without overflowing is 128, again minus 1. Now to figure out how big each element in our matrices can be, let's assume we have 2 matrices where m is the largest possible value we can store. That would mean our result would be in this form, and would then simplify to this. Let's do the same for 3 by 3 matrices. And this is what we get. Eventually, you'll see a pattern. That will relate the size of our matrix, the maximum element value that can be used without overflowing, and the number of bits we want to use for our values. For our 8-bit example, if our n is 2, our m would be 11. And if n is 3, our m would be 9. Hopefully it's obvious at this point the larger our matrix get, the smaller our maximum element value can be, which leads us to carefully think about using our memory. Now let's find out how much memory we need just to store our matrices. We need space for 3 n by n matrices and temporary space for our multiplications. So for a given n, we need this many memory addresses. Back to our 8-bits example. If we also use 8 bits to determine how many memory addresses we have, and then solve for n, at most we can only compute matrices up to 5 by 5. Visually speaking, this is our memory limit, excluding whatever else we may need to keep track of. But what if instead of using temporary space for matrix multiplications, we instead directly stored the sums into our result matrix C? That would free up some memory and allow us to increase our matrix size to 9. But we can do better. There's nothing stopping us from giving each matrix their own memory. So if we do this, we then bump up our limit once again. To get a better idea of what we needed to do next, why not just write a program to perform the basic matrix multiplication? And so we did. From this, we need to translate our C++ to assembly to figure out all of the operations we want to support. But before we do that, we can already see that there are ways to shrink this down. Here we removed function calls, but we can still shrink this down further. Here, we then remove the need to temporarily store the multiplications and instead keep a running total in matrix C. Now let's turn this into assembly code. First, let's load matrix A into memory. Next, we'll load matrix B into memory. And finally, we'll load matrix C with zeros. We're calling our memory load operation mload. The first number indicates which memory to use, the second number indicates what to load, and the third number indicates the address. There's a lot of duplication here, so we can reduce this down further by redefining some things. let's redefine what the numbers mean. Let's have the first number be what to load in memory A, let the second number be to what load in memory B, and let the third number be the address for memory A, B, and C, whereas a 0 will be loaded to memory C when mload is run. Next, we'll load register N with a 3. Then we'll initialize our row count with 0. And then our register for our column count with 0. And finally, we'll initialize register I with another 0. Next, we'll perform our matrix multiplication operator that we have just called go. Finally, perform our register increments and branching from them. And here is our complete assembly code. And here are the operations that we need to implement.
To save some time, we're just going to quickly flash through our block diagrams and maybe point some things out that are interesting, such as we have 2 ALUs, one for the register and one for memory. Register file. All registers are always outputting, so there's no need to select one for read operations. Register ALU. Our increment and branch less than n are implemented here. Memory. Each matrix has their own memory. Memory address selector. This is required to determine which element from each matrix to read from and write to. Memory ALU. Yep, it's that simple. And that is our Go operator implementation. Program counter. The only notable thing here is how we're using the most significant bit from our branch output to determine if the result is negative. This could have been implemented in a better way. We have control logic. And those are our block diagrams.
Last steps. Let's look at how we created our Verilog. We wrote 2 different versions. One, translating our C++ directly into Verilog. 2, translating our block diagrams directly into Verilog. I'll be going over the block diagram version. During our implementation, we were able to reduce our module count by combining functionality. On our first test run, we ran into a pipeline hazard and needed to create a new operator. We created a no-op because our branch less than operator was not getting the correct instruction file address if the branch succeeded. Here is a quick peek at our code. Now let's take a quick peek at our register code. Here's a peek at our memory code. Do note our else if go line. We'll need that for later. Finally, a peek at our test code. All right, here are our results. Note that this finishes in about 7.1 seconds. Now let's scale things up. But what does that mean? In terms of the GPU, that means more cores. In our case, we have our Go operator. Does that mean all we need to do is duplicate this circuit and we're done? Not quite. Duplicating the circuit also increases our outputs, which, according to our operation at the top, we need to store these summed results into a single output. So scaling for our circuit means handling more simultaneous multiplications requires additional additions added at the end. Let's bring back our Verilog code and see what needs to be updated to handle 4 simultaneous multiplications for this example, 4x4 matrix multiplication. Notice the added multiplications and additions. We also needed to update our increment for our I register to reflect our pseudo thread count. Now let's take a look at our simulation results. Note that this finishes at 3.2 seconds, and let's compare that to our previous simulation. 7.1 seconds. How did we verify our results? We consoled our results and plugged it into a calculator. Hopefully that's enough here to prove our architecture works. And if you think this is slow, our other version finishes at 550 and 200 nanoseconds. Final thoughts? There was one limitation we considered that would speed up our calculations more. This is from our C++ Verilog version. First, notice that we can only write to a single output at a time. We are able to read multiple memory addresses, but with output set up to write to a single memory address. Having multiple memory addresses to write to, hopefully, is an obvious speed up. And as an unexpected bonus, we wrote a Python script to generate our Verilog files to vary our threads, matrix size, and bit widths for our memory addresses and matrix element sizes. Please contact us if you'd like to know more.